All right. Welcome to another episode of White Paper Wednesday. My name is Jimmy Song, and this is the show that we do every Wednesday, reading through something that's a little bit more difficult technically as a way to learn more about Bitcoin. And, I do this show not just for you so that you can be informed, but for me. So I'm forced to read a lot of this stuff and really understand it so I can explain it to you guys. I have a really interesting one for you today. It is BIP340 updates. This is Peter Woola's post to Bitcoin Dev, and I'll share with you basically what he wrote, and we'll go talk about what it is that he said. All right, despite saying earlier that I expected no further semantical changes to BIP 340 to 342, I've just opened this pull request, and we can take a look at this pull request in a minute, to make a number of small changes that I believe are still worth making. Number one, even public keys. Only one change affects the validation rules. The Y coordinate of the 32-byte public key is changed from implicitly square to implicitly even. So if you were here for the BIP340 read through, basically one of the changes in Schnorr is instead of having 33-byte pub keys, as part of Schnorr you have 32-byte pub keys, saving a byte, but you implicitly derive the Y based on which one is square or not. That is now changed back to just implicitly saying that the Y coordinate must be even. And the reason for this is because, it makes signing slightly faster, like microsecond range, so it's not that much. Verification is negligibly slower in the nanosecond range. It also simplifies integration with existing key generation infrastructure, and that's the big one. Right now, basically anyone that generates a public key can do so fairly easily. You can just check the Y coordinate, and if it's odd, then you can subtract it from n and do something else, and so on. For example, BIP32 produces pub keys with known evenness, oddness, but squaredness would need to be computed separately. So adding that would have to change all of the HD libraries that exist, and almost every wallet uses some sort of BIP32 derivation. So to make it compatible, to make Schnorr compatible with all of those, going with evenness and oddness makes it a lot easier. Similar arguments hold for PSBT and probably many other things. And this is also true of PSBT, which is BIP174. Essentially, it's a lot easier to compute with compute evenness and oddness. You can compute squaredness by doing elliptic curve square roots and finite field square roots and so on. But it's trickier, and it's something that everybody would have to implement in addition, whereas this you can do much more easily. Note that the Y coordinate of the internal R point in the signature remains implicitly square. So that part of the Schnorr signature algorithm, which is the R point that's generated from the K, which is essentially the randomness that you use in order to create the signature. The R is the result of K times G, and that uses the Y coordinate that's implicitly squared. For R, the squaredness gives an actual performance gain of validation time, but this is not true for public keys. So the squaredness, because of the way the Schnorr signature algorithm is designed in BIP340, it makes you actually get a performance upgrade, and that's very important because every full node is going to have to check all these Schnorr signatures if they upgrade to Taproot. Conversely, for public keys, integration with existing infrastructure matters, but our points are purely internal. What he means there is that the R point is actually not used so much to be stored and things like that. It's essentially ephemeral. You create it once, and then you put it into the transaction, and then you throw it away, and that's that. So you don't need to have evenness and oddness because Schnorr essentially is like a whole new algorithm anyway, and implementing it is this is just part of the implementation work. Whereas computing a public key, that's already there for the most part, and this makes it easier. Nonce generation. All other semantical changes are around more secure nonce generation in BIP340, dealing with the various failure cases. So this is about that K value that generates the R, which is part of the Schnorr signature. So Schnorr signature is to find elliptic curve points over a finite field R and S. But R is purely random because K is random. Since dealing with the various failure cases, and nonce generation is talking about that K value, how do you make sure that that K value doesn't leak anything? Since the public key signed for is included in the signature challenge hash, implementers will likely be eager to use pre-computed values for these. Otherwise, an additional EC multiplication is necessary at signing time. The public key is included in the signature challenge hash. Implementers will likely be eager to use pre-computed values for these. So if you have a pre-computed public key, then it's easier to validate, and this again is important for running a full node. If that public key data happens to be gathered from untrusted sources, it can lead to trivial leakage of the private key, something that Greg Maxwell has started a discussion about on the Modern Cryptos Curves list. So if you generate it the wrong way, you can kind of leak the private key over time. And that's a big concern. You don't want to lose the private key ever. And if you lose the private key, there are all sorts of attacks that may compromise your money. So this is pretty important. We believe it should also therefore be best practice to include the public key also in the nonce generation, which largely mitigates this problem. So if you include the public key in the nonce generation, that forces the nonce to not be able to leak data. And this is an important part of protecting against certain kinds of malware. To protect against fault injection attacks, it is recommended to include actual signing time randomness into the nonce generation process. This was mentioned already, but the update elaborates much more about this and integrates this randomness into the standard signing process. So let's look up fault injection attacks. All right, so this is something that I don't actually know that much about. All right, fault injection. Fault injection is a testing technique which aids in understanding how virtual real system behaves when stressed in unusual ways. This technique is based on simulations or experiments result, thus it may be fault is a technique for improving the coverage of a test by introducing faults to test code spats in particular that might otherwise be rarely followed. I don't think that's about fault injection. Oh, okay. I'm not sure I understand that sentence then. To protect against differential power analysis, a different way of mixing in this randomness is used, masking the private key completely with randomness before continuing, rather than hashing them together, which is known in the literature to be vulnerable to DPA in some scenarios. So DPA, or differential power analysis, is looking at the voltage of something and seeing if it's high or low, and sort of gaining data off of that. This might be called some sort of like a side channel attack or something like this. A different way of mixing in this randomness is used, masking the private key completely with randomness before continuing, rather than hashing them together, which is known in the literature to be vulnerable. So you want to mask the private key completely with randomness instead of using that as part of like the addition for the hashing, because you can use differential power analysis to learn something about the private key. So you want to hide the private key as much as possible before doing that. That's essentially what he's saying. New tagged hashtags. To make sure that any code written for the earlier bit text fails consistently, the tags used in this tag in the tag hashes in BIP340 are changed as well. So he updated the tests and the tag hashes that were in BIP340, and that's what's in this pull request by Peter Woola. Number of changes here. Here's actual changes, and you know it's not very much. It's literally like a few words here and there. So computing a Jacobi symbol, test for squaredness. Okay, that's really in the weeds there. Implicit y coordinates are not a reduction in security, right? He justified that before. Y coordinate is even instead of a square. So instead of lift x, it's lift x square y, and there's he had to change a bunch of those in that pseudocode there. Freshly generated uniformly at random, so the secret key. Public key conversion, auxiliary random data. I mean it's a bunch of improvements along those lines. So there are some so there are a bunch of updates. I just wanted to read that through with you. Hopefully you can understand more of what's going on. I still don't really understand what a fault injection attack is. I'm gonna have to go look up some literature and read on that so I can understand it. If any of you do, please feel free to comment below in the video and so on. Anyway, hopefully that helped you and got you to learn a little bit more about Bitcoin. I try to do these videos more for myself than anybody else. So, Fiat Delenda Est, this song is done.